Hello, welcome to Lindorm. Today I will talk to you about the SediMeter SM4 and show you the basics of how to use it. In this end we have the underwater pluggable connector. So I will connect the cable here, make sure it's greased, and as you see here there is a blue LED that turns on to show that power is connected, and the green one shows the battery is charged in this. Next thing we need to do is to open the software. That's it. And when we open the software and the instrument is already connected, it will automatically do the connection, select the COM port. So we can go directly to the timing tab. The timing tab is where you can see the instrument time. You see the computer time here. It sets the instrument based on the computer. So if the computer is connected to the internet and a clock source, that's perfect. It will, as a default, show the time in UTC, but you can set it in local time for convenience. And then down here you see start time and interval. The start time is hour, minute, second. And interval is hour, minute, second also. So let's say we want to measure once every 10 minutes. Starting at midnight, that would be 000000. And then we click set. And when we click set, this button becomes active, start logging mode. So we can simply, well, let's check the UTC time, and we can see that midnight here in Sweden is 2200 UTC, correct. So we can now start logging, like so. And the instrument is now set up and will start logging once every 10 minutes at midnight local time. If we go to download, we can see that there are 6 records in memory. 6 total, 6 new. If we want to download, we have to stop the logging. So let me go back here and stop the logging. And to download, we first have to decide a file to put it in. So let me give a file name here. I'll just call it dummy. It automatically adds the extension LD2. And we have 2 choices. Download new data only or download all data. The convenient thing is to download new data only so that the file contains one session of data, to call it something. That means that you have an equal interval of measurements and there are no gaps. But in some cases, it might be necessary to download all data. For instance, if the instrument has had a reset, then the new data will be marked as old and you would have to download all data. So to download it, we simply click download here. And there we have the 6 records. And as you can see now, if we click check again, now we have no new records and 6 total. And now the red button becomes active, which means that now we can erase the memory if we want to. It's not necessary. You can keep writing. But it's a good idea to do it from time to time to clean out the memory. Because if you would have a reset in the future, then you would not have this problem of mixing old and new data. So let's go to look at the data now. We do that by going to the menu Data, Monitor and Display. And here we see the SediMeter plot. The SediMeter plot are these 36 optical backscatter detectors that measure the 180-degree reflected light, plus the 90-degree reflected light between them, in the 35 levels between them. So what you see on the screen now here is the straight backscatter And if we click here, we get the oblique backscatter. I'll press the adjust to adjust the grayscale. And if we click both, we'll get both the straight and the oblique. And since this is in air, the oblique creates a total reflection on the inside of the glass or polycarbonate. And that's why they get a much stronger signal than the straight reflection. If this is underwater, they should all get around 0 reflection. Actually, we can see this in color. If we go to SediMeter false color, I have to scroll to the left. And I'll have to zoom in a little bit to see it better. Here you see it's bluish, and the blue means that there is more oblique backscatter than straight backscatter. That is, it's in air. So blue means it's in air. If there is more straight backscatter than oblique, this graph, this false color plot, turns yellow. So that's a way to visualize the data that are hard to see in this striped graph. Now, if we go to the data plot, here we see the 6 measurements. They are 3 in the beginning and 3 in the end. So this is an XY plot where we can see the time of each individual measurement. Let's say we zoom in on this one here. Oh, there are 4 in the beginning, as you see. And here we have 2 close here. And on this side, we have the legend. So we have the temperature shown now, battery, light. To change the scale, you can double-click this one on value. It will change the scale to show all the data points. Let me get back to this later. But here we have the different sensors in the SM4. We have the level calculated in this application, the level that the instrument has estimated. And we have temperature in degrees Celsius, battery voltage, light in lux, the isoturbidity in FNU, the EPA turbidity, that's the US standard with white light, fluorescence 90 degrees and fluorescence 180 degrees. Let me show you here the scale. And then we have near infrared light, the background infrared light. We have the tilt of the instrument. If it's like this, it's 0 degree tilt. And if it's like this, it's 90, and like this is 180. And then we have the vibration. And the user is just something for real-time monitoring for reference. So the same data we can see here in the table form over here. See the date and time and the level and so on, all the way to the right. And now let me get into something here with vibration. You see, there is a 3-dimensional accelerometer mounted here. And it takes 30 measurements. For every measurement of the SediMeter, this one takes 30 measurements of XYZ acceleration. And it calculates the tilt as the average, but the vibration is calculated based on the standard deviation. Let's look at this here. Here you can see sample number 1, the acceleration in X, Y, and Z. This is the Y and the X. And we go here from measure. Here you can see there's a lot of vibration. Here it's been moving. I will get back to this in a second. So the last one is synoptic network data. This is for real-time monitoring. So let's go over to real-time monitoring. I would close this. Oh, by the way, the data we saved is available in raw data in this window here. I'll have to go to the beginning because I have the wrong number there. So here we have the 6 measurements that were in the memory. And they've been saved, so they're in this file here. But here we can open another file, import log file. And let's say we take, we can take this one. This is from an SM3 instrument that is mounted out in a duck pond here. And as you can see from this, the SM3 instrument doesn't have as many sensors. And in the data plot, you see here I will turn off the ones that don't exist. And this one doesn't really mean anything. And then we'll change the scale. And so here you see the level that the application has estimated. Let's look at the SediMeter plot. This is out in the duck pond, remember? And the level of the bottom is either here or here, depending on what you interpret as the bottom. But all of this is mud. It's mounted in mud. If I go out and put my foot in there, which I did when I mounted it, my foot will go through all of this. It's just D or jitja in Swedish. And here is a thin layer of something on top. So I would say probably this is the real bottom level. You can actually use this scale here, and change the color and change the scale, the contrast. Hey, doesn't want to let me grab it now. Ah, yes. And you can change the levels here, the values, manually if you want to. Let's say we put 6,000 FTU as the max. So that way you can also add new points here, add marker, to do the contrast stretch that you want. I don't know why this has a problem with grabbing onto it. The cursor doesn't want to, there, okay. Now let's say we do a very sharp contrast right there. So here is, if you want to get back to what it was, just do an adjust. And let's look at this in the false color also. Here you see it's below the bottom because it's yellow. And the black is in water. So yellow is down in the bottom, black is in the water, and blue is in the air. And here in the data plot, we have I'll take away the level. We have the temperature. It's been going up these days. This was in the beginning of May. This was from the 6th to 11th of May. So the cold weather ended here and we got a few warm days and the water temperature went up every day by about a degree. And we can see here the battery level. This instrument is mounted with a cable up on land. So at this date, on May 8th, I connected this laptop computer to the instrument, downloaded the data, and I had it connected for maybe 10-15 minutes, and the battery got charged. That's what you see here, recharge the battery. So if you do it like that and have the instrument connected by a cable that ends on land with another underwater connector, then you just bring this cable and the computer, connect it, download the data, and during the time you download the data, the instrument battery gets charged, and that's all the charge it needs. So we have looked at downloading data, and we have looked at opening an old file. Now let's do one more thing, measure in real time. But let's start with a blank screen. So I will close this and reopen it, but without the data. Now it's blank. And then we go to synoptic network data. This is the window for real-time measuring, real-time monitoring. This has 3 modes of real-time monitoring. The normal one is the one here in the middle. control network as master. In this mode, the computer sends the instruction to the instrument when to do a measurement and then gets the data back. In the first one, listen to network in logging mode, the instrument is set to log internally, and every time it logs data, it also sends it out on cable, and the computer is just listening and recording it on the hard drive. That obviously has the benefit that it's recorded both here and here. If the cable is cut, this will keep measuring and logging, so you won't lose the data because you lose the cable. If you lose the instrument, you still have the data that you already downloaded. So this is really double security, and definitely the best method to do for a monitoring project. But now let me show you the simpler one where the computer controls it. What we do then is set up the interval of measuring here. Let's put it at 1 minute. No, let's put it at 30 seconds. We'll get something more happening, or 20 seconds. Let's put it at 20 seconds, like so. I'll put it here so you can see it blinking. And now we go to monitoring and control network as master. But before I do that, if I would have just started monitoring now, it would have shown the data on screen, but it would not have saved them to the hard drive. If I want to save it to the hard drive, I have to select here the ID of the instrument. I haven't mentioned that. All the instruments by default have ID number 1. If you have more than one, then you need to assign individual IDs to the other one, but that's overcourse for now. So we put ID number 1, and then we have to select the file name to save it to, and let's save it to the same dummy file. It will add the new data, append the new data after the old data, so it will not overwrite it. That way you can write to a file, you can close this, you can reopen the file, and actually you don't need to reopen it, but you can, and then append data to it like this. You have to click log to file also for it to log. This you can turn on and off, but you have to select the file before you start logging. So before you start monitoring. Okay, now we start monitoring, control network as master, and you see this gauge shows up here, and here it says measuring, and it will do a measurement, and now it says next measurement in 12, 11, 10, counting down here. Up here we see isoturbidity, EPA turbidity for the US users, OBS turbidity, that's not supported by this instrument, and the instrument ID. Now it's done 2 measurements, so we can look at it in the data plot. And in the data table, we see it accumulating here, the data. Now, let's go to the burst sample. I will move it during the measurement. Let's see if I can get some. There. Now, here you can see that there are 30 individual measurements. And the reason the accelerometer was put in the instrument is to measure the tilt. Because in some applications, you can't dive down and put the instrument on the bottom. So you have to put it on a platform. And it can happen that the platform tilts over, something hits it. So therefore, the accelerometer is there. If the platform, if you put it on a platform, let's say it's a platform like this microphone, it tilts over. The accelerometer will tell you it tilted over, and you know not to use those data. Furthermore, interestingly, the fact that we record the actual vibration, 30 measurements and not just one measurement, means that it's been possible in actual field applications to guess pretty well what has caused it to tip over. If it's been a slow process, if it's been a fast hit. So in one case, for instance, we could say this is pretty sure this is a bear that's been hitting it with this, whatever they're called, ram. And in another case, we could see that this is pretty sure it's an anchor line that's pulled it over. So the accelerometer is a very interesting and useful thing. Now, here's another thing. When it's mounted down there and something hits it, the accelerometer is always measuring. And if something hits it like this, it will trigger an extra measurement. Not now when it's in real-time mode, but when it's in logging mode. And that's why another reason it's so good to have it in logging mode and listen to it. So this conditions-based monitoring is the reason why we could detect what it was that disturbed the instrument and in one case broke it off. Even when it was broken off, we could get the data out of it and we could figure out that it was a bear that had broken it off. So now let's look at our... If we want to stop now, we have to do stop control measuring, wait for the last measurement to finish, there, and then we can close this window. You can't close the window while it's monitoring. We get back here and I'm going to show you the last things in the control. We've looked at the timing and the download. The connection was the first thing we came to, timing, download. Then there's a second row. The network, each instrument has its unique number. This one, they all have come with programmed with number 1. In this one you can do a roll call and see which numbers are present on the network. And then we have the system tab. The system, here you can also set the logger mode. Set it to logger, like so. Set it back to sleep, like so. And you can change the baud rate up to 230,000. The last one here has a red button because this is really dangerous to change. This is the address of the instrument. As I said, number 1 is default, but here you can change it to another. And when you do, obviously you lose, you won't get a reply. Let's say I change it to 2. I don't get a reply because it I sent it out to number 1 and it came back from number 2. So down here it says send to 1, reply from 0. So if I want to communicate with this one now, I have to put it on 2. And then I can do get, and it works. And then I can change this back to 1 so I don't get confused in the future. And I change this back to 1 and check, and it works. And actually I'll go back to 9600 baud also so I don't get confused about that. And now it worked to change it. So, 1 tab left only, and that's clean. This instrument has UV lights here that are used to measure fluorescence, but also to prevent biofouling here. So if I don't look at the UV light because it's bad for the eyes, it can give cataracts. Use protective glasses whenever you are manipulating the UV light, and never look at it without glasses. So now I'll lighten up the upper one and the lower one. When it's mounted out there measuring, it can automatically do this blinking to keep it from fouling. And here is where you set the interval. You set it at something, let's say you set it at 100 seconds to start with. And then the instrument will automatically try to adjust it to the optimal value. So you set it like so. I'll put it back to 0. It's programmed so it will not blink when the instrument is lying down. It has a few features like that to try to prevent unintentionally emitting UV light when you have it on land because, as I said, the UV light is bad for your eyes. So I'll set it back to 0. Turn it off. That's it. And then we have in the menus, we can go through the menus. In the edit, we have this feature to see the raw data, open a file. We have the SediMeter list that I showed you. We have radio network. It's possible to connect by radio also. That's not the case now, so I'll just close it again. And it's possible to do a turbidity offset, but we won't get into that now. And in the advanced, here is the calibration. This is for us when we calibrate the instrument. And listen to calibration port. This is for users who are using another program to communicate. Then they can use this listen to communication port to see what's actually being sent to the instrument and received from the instrument. In the data, we just have that data menu, and there is nothing more except about pane, version number. The rest is in this monitor and display, where we have also the possibility. Oh, yes, I almost forgot an important thing, and that's how to get the data out of this. Let's say we open a file, raw data, and I import log file. We can take this one from the DAM again. Here you can export a text file with data. That's one way. Another way is from the data table, export as text file. It will export whatever is on this tab here. Well, I can click it, and you can select the name and export it here. And there is the feature of export data from this SediMeter. And then finally, you can also right-click in the graphs and so on in the table and do export here, images even. So there are a number of ways to export data from this. You have to try out the different ways and see which one is best for you. The data table only plots this. It doesn't plot the individual SediMeter data. If you want the individual data from this, then you would have to go over and do export data from this SediMeter here. All right then. And then we have the 3 modes there. We have share, we have view. Oh, there is a 3D view here that you can use to see the SediMeter data. This is a plot of the data from the SediMeter. The last value is actually from the SM3 is from one higher up. That's why it's completely different. And the network map. If you have more than one instrument, if you have a number of instruments and you give them coordinates, this map will just show you how they are located relative to each other. And that's it. That's all there is to it. All right. This was a rather long, brief introduction, but that's basically all there is to it. And any questions you have, you're always welcome to contact us, and we'll help you interpret the data. One of the things that takes a little bit of training is to learn to understand the SediMeter data, because the bottom is not like the soil, the ground, where it's either air or ground. The bottom between water and sediment can be rather fluid and can be very variable. So to understand the data from the SediMeter, you need to take that into account. And it's a good idea to look and check what kind of bottom you have, unless you have a sand bottom or something like that, of course. But if you have a bottom with mud and a soft bottom, you really should take a look at what the bottom is, so that you know what should I interpret as bottom. And perhaps you're not interested in the bottom. Perhaps you're interested in the fluid mud that's on top. So this SediMeter instrument is very useful for many things. And thank you for watching, and good luck.